Alright, so for the state population growth problem, I have my data. I've entered it into Excel because just because I have the data, I've got to figure out how can I model it so that I can actually do the comparison of figuring out when is it that Colorado will surpass Wisconsin's population. So if I highlight my data, and then I come up to Insert, and I want to insert a scatter plot, I can see that it does a really good job of highlighting the data and actually colorizing it so it's easy to tell. So I've got blue and red dots, and now I can actually start using it. So if I right click on my blue dots, which is Colorado, I can add a trend line. And when I do this, I want to make sure to display my equation as well as my r squared. And I can see that that's at 99 hundredths already. That's virtually 1. So that's a great equation to use. I'm going to keep that, and I'm just going to use that single equation. Here I'm going to highlight it, and I'm going to come up to home and make that a larger font so it's easier to see on my graph. Now I'm going to do the same thing with my red dots. I right click on a red dot, and I'm going to add a trend line. And when I do the linear, I'm going to, again, I can see that it's at 98 hundredths for my r squared, which is still a great equation, or a great coefficient of determination. But what I can also do, I can check the other ones. Exponential is pretty similar, logarithmic is pretty similar. If I go to polynomial, I do get it to be almost exactly 1. So since it's slightly higher, I don't need to go to this, but I will, just to look at it and see what's going on. And here I'll change this to go in here. We're going to highlight that, and we'll change that to 14-point font as well, so it's a little bit easier to see. Now, trying to extrapolate in Excel is kind of hard, so I'm going to take my equations and I'm going to put them in a graphing program. For me, I'm going to use Desmos. So I've got Desmos pulled up, and I'm going to just put the equations in, and you can see this one translated in perfectly because I got the squiggly there telling me that it's got the equation. Can't see it because of my graph where it's zoomed. It's not zoomed out far enough. And I'm going to do the same thing with the quadratic. And I want to show you something that's important to recognize. A few things when you graph these. So first, it says it doesn't understand it. That's because when I copied it, it doesn't copy the squared. So if I use the caret key and then hit 2, now I've got a graph. Alright, so I can't see it. So I'm going to zoom out, zoom out, zoom out, zoom out. Alright, now I can see I'm finally getting somewhere. And I can see that it crosses these two equations. And here's the thing I can start to pay attention to, be like, this doesn't make sense. What is going on? Because 2000 is the year 2000. So they're saying that based on this, it won't meet until almost 2484. Like, that doesn't make sense. And so the question is, well, what's going on? So if I go back to my data, the thing to remember about my equation that I get, or that is provided by Excel, is that they are rounding. So I need to be able to format this. So I'm going to go Format Trend Line Data, and it does general as the normal way. I need more decimal places. That's the problem. So I'm going to go to Number, and I want to do, say, 6 decimal places. Now you can see it didn't do it, so I'm going to, and sometimes this happens and it's okay, you can delete that box, and I'm going to right click and I'm going to Format Trend Line again and make sure I display the equation and display the r squared. But because I changed it to 6 decimal places, when it redid that box, you can see that I now have the 6 decimal places that I was hoping for. So I'm going to copy this equation, because you can see this is much more exact than the equation I was just dealing with. And if you think about the fact of we're dealing with our x values being in the thousands, we need to have as accurate as possible. I could take this out even more decimal places if I really want it to be accurate. But I'm going to copy this, and I'm going to replace this one with my new equation. And again, it tells me, hey, something's wrong. What it is, first, I'm going to replace, I use the caret key, so that's Shift 6, change it to squared. It's like, oh, you still got something wrong. Well, the problem is here it's got this comma for 4000. I need to delete out any commas. Now I have something that I can work with. And you can see, okay, now this looks a lot better. So let me see what's going on. And do I get an equation, a point where they actually cross? And it's actually back at 1990. So that doesn't seem to make much sense either. So then I'd say to myself, okay, maybe even though it does a great job of graphing, maybe this isn't the best model for Wisconsin. Maybe it's not doing a good job of predicting what's happening because it's saying that I should have already surpassed them. So what I'd want to do then is say, okay, this is not a good model. I'm going to reformat this into something and see if I get a better model that fits the data better. So I'm going to go into my linear. And again, linear is really high. So I'm going to copy this equation, place it over here. And if I look, it says at about 2026 and 2027, these two should cross. And that seems to make a little bit more sense than what I was getting before with the quadratic. So even though you may have a higher coefficient of determination, you have to think about, does what it project make any sense with what's going on? In this case, the quadratic, while a higher r-squared value, was not a better predictor. More likely, using the two linear models is a much better model overall.